In this lesson, we will discuss multiple regression. This widely used technique empowers researchers to scrutinize the connections between a dependent variable, known as the response variable, and several independent variables, known as explanatory variables. The use of multiple regression spans across diverse biological research fields. Some instances include, in genome-wide association studies, multiple regression is frequently used to pinpoint genetic variants linked to various traits and diseases. Ecologists can use multiple regression to examine the relationships between species abundance and various environmental elements such as temperature, precipitation, and habitat features. Multiple regression can be used by researchers to investigate how distinct factors like diet, exercise, and genetic predisposition affect physiological attributes, such as metabolic rate or muscle strength. In epidemiology, multiple regression is commonly used to identify disease risk factors and evaluate the relative contributions of different variables, like lifestyle, environmental exposure, and genetic factors to disease development. We're going to begin with some definitions. A response variable denotes the quantity we want to predict. It's most often represented by y. Explanatory variables represent the various factors that may influence the outcome of the response variable. These variables are denoted by x1, x2, x3, and so on. Now, if there are p explanatory variables, the multiple regression is given by y equals b0 plus b1 times x1 plus b2 times x2, and so on until we get to bp times xp, where b0, b1, b2, and so on are constants. Okay, let's dive into an example. We have a study in which the lung capacities of 16 children were measured. Variables that might be useful in predicting a child's lung capacity include height in inches, weight in pounds, and age, as well as the temperature in degrees Fahrenheit and barometric pressure at inches at the time the lung capacity was measured. The multiple regression equation for lung capacity takes the form y, which represents lung capacity, equals b0 plus b1 times x1. Here x1 represents height, plus b2 times x2, which represents weight, plus b3 times x3, x3 represents age, plus b4 times x4, x4 represents barometric pressure, plus b5 times x5, x5 is temperature. Now in R, let's demonstrate this by loading the lung capacity data into R. We will store the data in a variable called lung study, and attach the dataset to our workspace, making all variables readily accessible. Next, we enter the lm command, followed by the response variable, which is lung capacity in this case. Then we use a tilde and add all the explanatory variables, height plus weight plus age plus barometric pressure plus temperature. The left side of the tilde represents the response variable, while the right side is the sum of the explanatory variables that we want to include in the model. I'm going to save the multiple regression model into a variable named model1. Then we can pull it up to see the results. We obtain the coefficients b0, b1, b2, b3, b4, and b5. Our predictive model for lung capacity is y equals negative 7.81721 plus 0.11927 times x1 minus 0.02463 times x2 plus 0.16411 x3 plus 0.07640 times x4 plus 0.02022 x5. Now suppose we wanted to predict the lung capacity for a 61-inch tall, 105-pound, 12-year-old individual in a location with a 30.1-inch barometer pressure and 70-degree temperature. To make the prediction, we input these values into the equation. Now, we can directly input the explanatory variable values into the equation, and this yields a predicted lung capacity of 2.556. If you're doing multiple predictions, an alternate method may be easier. We can first call the regression equation coefficients using the coefficients command. Next, we create a data array with 1 as the first value. This corresponds to the constant in the equation, and the explanatory variable values. We have a data array consisting of 1, 61, 105, 12, 30.1, and 70, and I'll call this new data. Then we'll just calculate the sum of the products of the coefficients and the data array. Again, we get a predicted lung capacity of 2.556. Now that we've seen how to do a multiple regression model, let's discuss how to determine whether multiple regression is appropriate in the first place. One method is to analyze a residual plot. For each individual, let y hat be the predicted values based on the given explanatory variables, and let y be the actual value of the response variable. The residual for each individual is the value y minus y hat. A residual plot is a scatterplot of the predicted values and the residuals. In R, we create this plot using the command plot fitted model1, resid model1. When multiple regression is suitable for modeling a scenario, the residual plot will not display any discernible pattern, such as a curve or a line. For the lung capacity model, no noticeable pattern is observed, indicating that using multiple regression is appropriate here. Let's talk about testing multiple regression coefficients. The 16 individuals in our lung capacity data represent a sample from a larger population. When we compute the multiple regression equation for this sample, it estimates the multiple regression for the entire population. The sample's multiple regression coefficients are B0, B1, B2, and so on. Suppose that the population's multiple regression equation coefficients are denoted by beta 0, beta 1, beta 2, and so on. Here, B0 estimates beta 0, B1 estimates beta 1, and so forth. When one of the beta coefficients is equal to 0, the corresponding explanatory variable has no relationship to the response variable. As part of the multiple regression process, most statistical software will automatically perform a hypothesis test to determine whether each beta is non-zero. The p-values of these tests are listed as part of the summary of the model, which can be obtained with the summary command. This approach helps estimate which explanatory variables contribute most to the prediction. In the lung capacity example, height, weight, and age have small p-values. We conclude that the beta coefficients corresponding to those variables would be non-zero, indicating that these variables significantly contribute to predicting the response. Note that barometric pressure and temperature have larger p-values, suggesting that the beta coefficients may be equal to 0, which means that these variables may not be as important in predicting the response. Generally, the objective is to identify potentially unnecessary variables. Okay, I'm going to rerun our model using only height, weight, and age. We will call this Model 2. In this model, we see that the p-values corresponding to each explanatory variable are all small, meaning that each variable plays a significant role in the predictions. Let's consider again predicting the lung capacity for a 61-inch tall, 12-year-old individual weighing 105 pounds. We will create a new data array, including only height, weight, and age, plus the 1 at the beginning corresponding to the constant term. Now, multiply the coefficients of Model 2 by the new data array, and then take the sum. We find our prediction to be 2.520988. So we have found two models for predicting lung capacity. Which is better? Unfortunately, there is no straightforward answer to this question, but we can check a quantity to help us narrow in on one. Without going into detail, the output includes a quantity that measures how well the model fits the existing data. This quantity is the adjusted R-squared value. A basic principle when building multiple regression models is to aim for the highest possible adjusted R-squared value. When we apply this principle, we find that Model 2 is better than Model 1, because Model 2's adjusted R-squared value is larger. Between observing the p-values to determine whether the various explanatory variables contribute significantly to the prediction and observing the adjusted R-squared values, you can often come up with a good, minimally complex multiple regression model that effectively predicts response variables.